we end up doing a lot of integrals over disks, and it turns out that luckily enough, a disk is an elementary region both ways. So let's just think about how to set that up. So if we take the disk like this, right, and we want to do the integration vertically first, so thinking about it being sliced up like this, then we say, okay, so where do we start? Well, we start, here we'll do green for go. So we start along this curve, and then we stop on this curve up here, right? So each one of these slices, if I pick some random x coordinate, so there's x, we're going from bottom to top like that. And so we think, okay, so the curve that we start at down here at the bottom, this is going to be, I didn't tell you which disk this was, sorry. So I'm thinking that this is just a unit disk, x squared plus y squared equals 1. Okay, so then the curve for this bottom part here, we find just by solving for y, and we see y is minus the square root of 1 minus x squared, and so we take that as our c of x function. And similarly, we take the top curve as the positive square root of 1 minus x squared. So that will be our d of x function. By the way, the c and d, that's just dummy notation. I mean, you never actually use that. I'm just using it right now to describe what we're talking about. Okay. So then I would take whatever my function is, the integrand that I want to integrate, and I would say, okay, so we are going to go, let's see, from y equals minus square root 1 minus x squared up to y equals positive 1 square root 1 minus x squared. And that's going to be dy. And so just think about what will happen when you evaluate this. You're going to integrate y, and then you're going to evaluate y, and then you're going to have nothing left but functions of x. That's important. So once this part here is integrated, so after evaluating this, only x's remain. Okay, and so then when we go ahead and we integrate those x's from x equals, and then we go back to our disk and say, okay, so where do these slices begin and end? Okay, so we have our first slice right here. It actually consists of only a single point, but remember, it's okay for it to be a single point. And then the last slice happens here, and again, it just consists of a single point. But this goes from x equals minus 1 here to x equals 1 over here. So we go from x equals minus 1 to x equals 1. Let me just make that blue so it's all matchy. There we go. Okay, so that is how we would set it up as an elementary region, the first type, or that type, whatever. And you can see just by the symmetry, well, that's the least symmetric circle I've ever drawn, but okay. So you can see by the symmetry of the disk that we could do exactly the same thing, this time starting on the left. So that's our starting curve. And when I say starting curve, I just mean if you imagine anything going from left to right, zap through the object, where's the first place that it hits, where's the last place that it hits, that tells you what your starting and ending curves are going to be. And so now each of these is, we can understand it as the graph of a function of y. For a particular y value, we know that we're going to be starting on one and then moving toward the other one, left to right, yeah? And we have different lengths for different y values, but that's what the game is all about. Okay, so we're going to be going from now on the left, we have our a of y, which is, going back to the same formula, going to be the negative square root 1 minus y squared. And over on the other side, we have our b of y, our ending zone, which is going to be the positive square root of 1 minus y squared. And then we pick these slices up from our first slice down here at y equals minus 1 to our last slice up here at y equals 1. And again, each of these is just a single point, but that's fine. So let's see, so whatever that integrand was, we started by integrating it from the left bounding curve at x equals negative root 1 minus y squared, and we integrated it up to where x is equal to positive square root 1 minus y squared. And we were integrating dx because these slices are parallel to the x-axis right here. Okay, and then once we've done that, this expression, so just looking at this algebraically, once again, this expression right here, if we integrate with respect to x and then evaluate x at these expressions that have no x's in them, then by the time we're done, after evaluating, only y's remain. So that when we next integrate with respect to y and evaluate from y equals minus 1 to y equals 1, then all that will be left when we're done is a number, a constant, a scalar value. And that's really an important thing that I'm sort of trying to pound on, go on and on about, whatever, because you should never, ever have variables left after evaluating both integrals, right? So this means in particular that you should never have any variables in the outer bounds of integration. And in case you're wondering why I'm beating on this dead horse, it's because this is like the most common mistake that I see. Like we'll be doing problems where I'll say something like, okay, take one of these integrals that we've just done. So something like this, and I'll say, now set this up with the order of integration exchanged. So in other words, swap this so that you're doing dx first. And I'll see something like, somebody will go, oh, okay, it's just this. And that is just completely wrong. 0 points, no checks given. This indicate if you have this kind of thing going on right here, where there's variables in the outer, that's what I mean by this, variables in the outer bounds of integration, that means that you are completely not understanding what this notation means and what is going on, because this over here, this is just nonsense. So I want you to avoid making that mistake. It's real easy to do though, because we just did that little mini chapter on double integrals over a rectangle, and you think, oh, I just swap the things and keep the outer ones on the outside and the inner ones on the inner side. But like, no, that's for rectangles. That's when everything is bounded by a constant. You can get away with it there. Here, you have to really think and map out your region before you set it up in the other direction. And there's no quick substitution method. Like, students often want to like find the technique for that is just do this, solve for y, and then stick it in, and ta-da! It's gonna cause you trouble. You don't want to do that. You want to draw the picture, think it out, understand the concept. And the other thing, and this is minor by comparison, but notice that we don't mess with the integrand. So no matter how you set up the integral, the bounds of integration will change and might get complicated depending on how you're changing it from one thing to another. But the integrand is exactly the same. You don't have to rewrite you want to keep the integrand exactly the same no matter how the integral is set up.